Um, hey everyone, this is Sam. Today I'm going to discuss about basics for mathematics for machine learning, uh, which we call it as MML, mathematics for machine learning. So in this, first we need to see basics here. So further we need linear algebra. First basic is linear algebra, and we get into probability and statistics, and then discrete mathematics, and some part of machine learning like artificial neural networks and etc. something. But I will deal with the mathematics part. It is must and should we have to know like what is the background, mathematical background for machine learning. So now we will look into what is the basics of linear algebra. We usually deal with matrices, vector spaces, and matrices and its operations like finding determinant, rank, or dimension, finding eigenvalues, vectors, and everything else, and vector spaces. So first of all, let me start with vector spaces. What is a vector space? What is a vector space? So we know that what is a space? Space means something, it has collection of objects, right? Some collection of objects, let's say a set. First, I will tell you what is vector space. Then I will go to what is vector space. Generally, they say that it is a set which is closed under addition and scalar multiplication. But I do not I don't like this way. But what I say is vector space. So here I'm introducing some algebra. So vector space is a set two operations. So what are these operations? That is addition and multiplication. So if we take a vector, if we consider a vector V, vector space V under addition and multiplication is a set B with two operations, addition and multiplication, which satisfy these following axioms. That is under addition, V is a group, and under multiplication, V is a group. So let us see like what is addition. So what is this? V is a group under addition. That says that. So if it is a group, then it must satisfy four axioms. What are those? Closure, identity, and inverse should exist. So one property, and when three properties. And since we are saying V is a group under addition, so then it must satisfy addition closure, which is, suppose if we take V or vectors which belongs to this capital V, then U plus V, so the result of this also should belong to V. So that is the addition closure. And second thing is identity should exist. So if we consider 0 is 0 belongs to vector space. So whenever a vector is added with 0, then it gives the same vector, and either ways also equals to these all. So we know that small v belongs to capital V, which is vector space. So we can say that this 0, which is identity, exists. Well, and when coming to inverse existence, so for we here consider additive inverse. Since we are doing group operation under addition, we consider additive inverse. So what is additive inverse of A? What should be here so that it becomes equals to 0? Obviously it is minus A. A belongs to V and 0 also belongs to V, and either ways minus A plus A equals to 0. That means this minus A belongs to vector space. Since A belongs to V and this 0 belongs to V, since we have already found out that identity belongs to vector space from the above thing. So in the same way, this is also belongs to V, which is inverse. So we can say that inverse exists. Now comes to fourth property, associativity. Here C plus D, if all C comma D comma E belongs to vector space, all these vectors belongs to vector space V and E, that equals to C plus D plus E. So this is associativity. And even this also, so what if we do, so since all these belongs to V, then all and the same, and the resultant also belongs to V. Here also same, the resultant also belongs to V. So it says associativity. And whereas if the property is actually vector space is abelian group, that means along with four axioms of group, it also satisfies commutativity. Okay, so the fifth property we discuss here is commutativity under addition. A plus B equals to B plus A. So this belongs to V, or we can take U plus V equals to V plus U, since we already consider U comma V belongs to vector space V. So this resultant also belongs to vector space V, and this also belongs to V. So we can say that it is commutative in nature. And other property is distributivity. These are special property. We can come to this later. So this is like special properties which is not considered here. So let us take, since we also told that vector space is group, or say abelian group under multiplication. That is, so group means has 4 axioms, and whereas abelian group has 5 axioms. So which is closure, identity exist, inverse exist, associativity, and commutativity. Okay, so we'll discuss. So multiplicative closure, let's take this 6 multiplicative. So in addition, we have seen that if A belongs to V and B belongs to V, then its resultant also belongs to V. So if this happens, then we say that it is closure under addition. And here the same way in multiplicative closure also we consider multiplication. If A comma B belongs to vector space V, then A dot B or A multiplication B or if is also belongs to V, then we say that so it satisfies closure property satisfied. And whereas now we find identity. So in addition, identity is 0, whereas in multiplication, what is identity? That means when you do when you perform some operation between two vectors, the same whichever vector, either this or that. I'm taking A. So in addition, we got A plus 0 equals to A. So here in multiplication, A dot something must equals to A. So what is that? One. True? Yes. So either ways also 1 into A equals to A. Since A belongs to vector V and this resultant also belongs to vector V, that means the whichever we multiplied should also belongs to V. That means 1 belongs to V. So this is multiplicative identity exist, right? And coming to the next, so multiplicative, what is this? Multiplicative inverse. So in addition, we have seen multiplicative, additive inverse, like A plus minus A equals to 0. That means A plus something should be equals to identity, like some under whatever, like additive identity. So here additive identity. So here also A into something should be equals to multiplicative identity, that is 1. That is A into something should be equals to 1. So what is this here? That is 1 by A. So if we cancel, we get 1. So A into 1 by A, or we say A into A inverse equals to 1. And either way, A inverse into A equals to 1. So since A belongs to V and this resultant belongs to V, we have seen the above thing. So that means A inverse also belongs to V. That means inverse exists. So till now we have satisfied 4 axioms of group under multiplication, but we said this is a abelian group under multiplication. So we have other, and we forgot to prove associativity. Let's prove that, and let's jump to this associativity. That means A into B into C equals to A into B into C. Okay, so either ways it could be anything. And so since this is abelian group, commutativity, A into B equals to B into A. Since A belongs to V and B belongs to V, so this resultant belongs to V. if if this whole product has the same resultant, then if it is belongs to V, then we say that commutativity under multi. So till now, how many things happen? So this is the ninth one, and this is the 10th one, and there I told some special axioms also there, like distributivity. Distributivity that says that C plus D into B. So here C and D are scalars and B is vector. So then that gives C into V plus D into V. Since D is scalar and this also belongs to vector space D, since D is scalar and multiplied with this belongs to V. Since these two belongs to so the resultant also belongs to V. So we say that the resultant should belong to the vector space, then only we consider it as a group. So and the other thing is distributivity. Yeah, this is 11, this is 12. So I'm taking one scalar multiplied with addition of vectors. So u comma v belongs to vector space, that means these two are vectors, and this is a scalar. So when it is multiplied, then it becomes C into V plus C into V. Since this is belongs to V and this also belongs to vector space V, the whole thing belongs to vector space V, and here also the whole thing belongs to vector space. So undoubtedly the addition of this belongs to vector space V. Okay, that's it. So here we all discussed what is a vector space. Okay, so what is a vector? We actually need this. What is a vectors or elements of vector space? So the elements of a vector space are vectors, and they strictly follow addition and multiplication operations. Okay, it has some rules. It follows some rules of addition and multiplication vector. These are generally either column matrix or row matrix. Okay, first I'll come to what is matrix. Matrix is a set of system of when a linear equations, a system of linear equations is written in a matrix form. So what is a vector? Vector is something which has magnitude and direction. It has magnitude and direction. So if we like, that is length, and it has direction, or whether this or this. So this length, this is magnitude, that means it tells length, and this also length, this is how much is length. So that is magnitude, and the direction, the arrow indicates which direction it is, it is following. So basically vectors are 1 by n or n by 1 matrix. So generally they are 1 by n, that means one row and n columns. And what is this here? N rows, one column. We generally denote vector with vector v with this way: v1, v2, and so on, vn. In mathematics, we do not put more than 3 dots, like and so on. 1, 2, comma, 3 dots, and that is, we should not put how many dots we want to. So only 3 dots. We limit only to 3 dots. Okay. So here also, like general, this is what is this called? This rows, columns. So what are rows? If you take some classroom, we tell how many rows are there, how many columns are there. The horizontal counting 1, 2, 3. There are 3 rows. Let us take some other row also. 4 rows. We say there are 4 rows. And here also, second row also there are 4 rows. I mean 4. Sorry. No, this is wrong. So how many horizontal extents are there? There are 3 rows. That means horizontals. So how many verticals? 1, 2, 3, 1, 2, 3. So these are columns. So basically matrix which we represent inside a square bracket, we write A, B, C, D, E, F. So these are rows. How many rows? 2 rows. And these verticals are columns. How many columns? 3. So what is order of this matrix? 2 by 3. Always we should first write rows and then columns. Okay. Columns cross rows, rows cross columns. This is the correct order to represent a matrix. So what were we saying? Vectors are, so see how many rows are there? 1, 2, 3, and so on, n rows. So first we write rows and then columns, right? So how many columns? Only one column is there. So n cross 1. These n cross 1 order matrices are called vectors. Okay. You can also write like this: v equals to v1, v2, v3, and so on, vn. So these are columns. We have n number of columns. We should rows in columns, so n number of columns. And then how many rows are there? Only one row. So 1 cross n. Okay. This is something. Here's something. So this is a vector. How many rows? A number of rows and one column. So we call this as column matrix, which has only one column and any number of rows, irrespective whatever this number is. But if you have only one column, then we call it as column matrix. And if we have one row and any number n number of columns, so we call it as row matrix. So this is a row matrix. So this is a vector. We also not in this way also v1 v2 v3 and so on vn. We can also do that. So we have some right. We have some properties which this follows. So I will discuss this in the next class. So see you. This is Sam, and I will call it a day. Goodbye. Bye.